So first, I would like to thank the organizers, especially Christoph, also Ramon and Gilbert for inviting me for first one presentation, and then a few weeks after 2 presentations, and at last 3 presentations. So this is the first presentation. This is on strength and toughness of ceramics. So some aspects were already treated by Gilbert Fantozzi, but we will go in more details in some aspects. And the idea is to think if it's possible to apply strength and toughness ideas on nanoceramics and also on nanocomposites. So this is the outline of my first talk. So I just want briefly to give you some advantages of ceramics, since after a few minutes I will talk about the main drawbacks. So I will take 1 or 2 minutes to give you some advantage of ceramics, and especially on the domain we have investigated in the nano-scale project, which is biomedical applications. And then we will talk about the major drawbacks of ceramics, which is, as we know, brittle failure. So brittle failure of ceramics, and especially for biomedical applications, is not an option, as could say the NASA some years ago. So we talk about ceramics, behavior versus metal and polymers, the role of flows on the strength of ceramics, so the same topic as Gilbert told before, but I will insist really on the defects we can find as a function of the process we have made. And then the strength-toughness relations. And especially I would like to insist on the third point: what are the flows in ceramics? What are the flows which are generated by the process? Gilbert said that processing is important, so we will give you some examples of flows generated during the process. And we'll take the example of thermal heads, which are used for hip components. And then how to increase the strength, how to increase the toughness of ceramics. So how can we play on the strength-grain size relations, strengthening, toughening, and does it apply to nanoscale ceramics and composites? So this is the idea of this presentation. So first, just some advantages of ceramics for what we are looking at. We know that ceramics are very hard, so they have a good wear behavior. So if the wear behavior is better than that of metals or polyethylene, you generate less debris when you are wearing 2 parts, one against itself. And when you have a hip prosthesis like that, one part is wearing against another one, so the thermal head is wearing against a cup. And this is an example of metal against polyethylene coupling, and this is just after placing the prosthesis inside the body, and this is 12 years after placing the prosthesis in the body. And people who are not familiar with this say, okay, everything works properly after 12 years, the prosthesis is still here, nothing is broken. But in fact, you have quite a large amount of bone loosening at the interface with the implant here and in this area, and this is due to the wear debris generated by the coupling of the metal against the polyethylene. And looking carefully at what we see here, you can see that the ball has entered inside the cup. The cup has worn, the polyethylene cup has worn. So wear means wear debris, and these debris are critical for inflammation. So they lead to inflammation, and they will lead to aseptic loosening. So today we think that the best solution is using a ceramic against polyethylene, or even better, a ceramic against a ceramic. So for example, these are wear quantities in terms of weight loss of different coupling systems versus the number of cycles. We do approximately 1 billion cycles per year. So every year you make 1 million of cycles. So it can be considered as a 5 years trial. Here is the metal against polyethylene coupling, high wear rate a large weight loss of polyethylene, of course. These are for 28 millimeter heads, so quite large heads. For lower size, you decrease the wear debris generation. But if you take a ceramic, here it was zirconia against polyethylene, for the two same diameters, you still decrease significantly the wear debris generation. And when you now talk about ceramics against ceramic, there is almost no visible significant wear. So ceramics are interesting for us. I see some people from Nobel Biocare in the room, so I cannot resist to show you this kind of photo. It comes from a presentation of Ramon at the beginning of the project. So, of course, ceramics are also interesting in dental applications since they are inert, and of course they are aesthetic. You prefer certainly this to this kind of face, of course. So they have aesthetical advantage for dental restoration, and also there is a tendency today towards no metal in some countries. So ceramics are interesting, but we have to face brittle failure. So of course, for biomedical implants, I would say failure is not an option. Of course, when you see something like that, you are not happy with this kind of failure. This is failure of an alumina hip thermal head component, and this is failure of zirconia thermal head inside the body. So of course, these are critical events, but they do not happen a lot in ceramics today. If we took, for example, failure rate in the 70s to the 90s, it could be from 0.2%, but Balox product from Ceramtech, they claim 0.2%, up to more than 10% failure ratio. So that was really high and unacceptable. In the 90s and towards 2000, there was a decrease in the failure rate. And what is the state today? At least Balox producer claims that the failure rate is below 0.02%. So that's quite low, but our ceramics are now limited in terms of designs, especially for alumina ceramics. We don't want to use less than 28 millimeter heads. And that's a problem due to the fact that for lower size of the thermal heads, there is a risk of failure. So we don't want these low thermal heads designs. So we were talking about toughness with Gilbert. The toughness of alumina is only 4 megapascal square meter, and zirconia has a larger toughness, let's say about 6 megapascal square meters, so much less than metals, but we will go towards this aspect after. So this was given by a dentist, a friend of mine. Here is an abutment, a zirconia abutment, and after trying to put this screw to fix the abutment, there was a failure of this abutment. So something happens sometimes in some occasions, and we do have some failures of implant in the body. Of course, failure is not limited to ceramics. It also happens also in metals, especially due to the fatigue. And I have, for example, one example of really a critical event that happens in the 90s on cardiac valves. So cardiac valves does really cyclic fatigue. Every second you heartbeat, and every second you have a cycle. So this part is doing this kind of movement. And so it mechanically loads this strut. And for one specific cardiac valve design, which was called Bjork-Shilley designs, they were really widely used in the 90s. There were some problems here, failure due to cyclic fatigue. And of course, when you have a breakage of cardiac valve, it can lead to really critical events. So in a short period of time, there were 600 failures for more than 80,000 implanted prostheses. So we can say the failure ratio is only 1%, but it was fatal on 2/3 of the implant. So again, of course, especially for biomedical application, failure is really unacceptable. So Gilbert has already showed some aspect of the difference between metals, polymers, and ceramics. So I just want to insist on some points and maybe to visualize the difference. During my talk, I will just start this movie, and you will see that if it works, it should work. Okay, so the movie is going on, and you will see that there is no strain before, or no visible strain before breakage. So I'm loading this ceramic part under 4-point bending tests, and so I am increasing the load more and more. So the load is increasing, but you cannot see anything, and then it breaks. So that's the typical behavior of ceramic. It breaks without any significant macroscopic strain. So let's say the curve is applied force, the deformation. You have a straight line like that, very steep, since the Young's modulus is large, and maybe high stress to failure, larger than some polymers and also some metals, but the strain to failure is very low. If you compare that to a polymer, you will see that for small loads, you will have large deformation. So there is a big difference between metal polymers on one side and ceramics due to the fact that the strain to failure is really low. So we have hard materials. Is it working? It should deform, huh? Yes, I think it's now, okay. So we have hard materials, stiff materials, but they remain really brittle. So we don't have to confuse between hardness, high, stiffness, high, but brittleness, and low strain to failure. So you can see here the polymeric material, which is straining a lot. And so you have a large deformation to failure. Okay, so we have seen this short movie, and what we have obtained is stress, 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 applied stress, strain curve like that. So it's a linear plot, and then there is breakage. So it's difficult to predict the failure of ceramics, and sometimes we hear the term, we have unpredictable failure. You take the same ceramic, two components, two parts, two different specimens. One specimen will break here, the other will break here. So is it possible to predict the failure of ceramic? That's the first point. The second point is, of course, as it was said also by Gilbert, the energy to failure is really low as compared to metal, since we have only elastic energy which is stored before the failure. But when we look carefully at samples, parts, and so on, there is always a flow at the origin of the failure. So we cannot say the failure is unpredictable. The failure is quite distributed due to the distribution of flows. So we have to keep in mind that we have always a defect at the origin of failure. So for example, here is a 4-point bending test, and then we have breakage. And looking carefully at the surface of failure, we can see a flow, we can see a pore here. So we have to take into account the flows. So if we have large defects, the strength will be low. If we have small effects, the strength will be much higher. And we can imagine, let's imagine, that we have no flow in a ceramic. You should have very, very large strength. And here is an example, which is quite old example, but really, really spectacular example of a glass fiber which has been strained towards 7.5%. So large deformation and no breakage. And the stress here is of 5 megapascal. So this small glass fiber without defect or with very, very small defect can resist high stresses. So really, strength of ceramics is directly related to the presence of flow. So I would say that a glass, just to give you an image, a glass fiber of only 1 square millimeter would support 26 kilonewtons if it has no defect at all. So we have always defects, unfortunately. So let's talk about stress concentrations around flows. So the cleavage stress. So the cleavage stress is the stress necessary to separate two atomic planes, can be calculated, evaluated. So in the past, it was evaluated with, let's say, some hypotheses with analytical models. It can be now evaluated from atomistic simulations, and they quite agree. So the idea is, what is the stress necessary to separate two planes of a given ceramic, of a given ceramic structure? So you can calculate that for alumina, the stress necessary to separate two planes, so to have cleavage, is about 40 gigapascal. So the real strength, intrinsic strength of the alumina is 40 gigapascal. And in fact, in the best cases, in practice, we only have, in the best cases, very best cases, 800 megapascal. So there is an apparent discrepancy between the stress needed to separate planes, so to have a failure, and really what we obtain experimentally. In zirconia, that's the same. We should reach 20 gigapascal. So in some location of the ceramic near defect, we reach 20 megapascal, while the experimental measured strength is about 1 gigapascal. If you take a glass window, the strength is 200 megapascal, while we should reach, in some region, 7 gigapascal. When you take a glass fiber with less defects, smaller defects, you can reach some gigapascal. So these apparent discrepancies must be explained in terms of presence of defects that lead to stress concentration. So for an applied stress of 100 megapascal in some region near flows, you have much larger stresses. So this is explained by what we call stress intensity factor, and then we have to relate this to the toughness. So what we say is that for an applied stress, an applied external stress, which is sigma, around the defect, so imagine there is a crack here, so there is a pre-existing flow. Around this flow, there are very large stresses. So the stress field can be calculated here, and what we see from elastic calculation is that the stresses all around, so the tensile stresses, also the shear stresses, are very large in the vicinity of a crack. So I take this paper with my students, so why not with you today? Here is a crack. I have applied 100 megapascal, but here in this region, near the crack, there are stresses much, much larger than what we have applied in the overall pieces. So take an example. You apply 100 megapascal. Here you have gigapascal at the vicinity of a crack. And so we have a factor which is called the stress intensity factor, K1. The name is correct. The stress intensity factor means what are the stresses in the vicinity of the crack. And we can calculate this stress intensity factor, and it is given as a function of the applied stress. If there is no applied stress, there is no local stress here, but also a function of the crack size, and also a function of the geometry of the crack. But let's say this is a geometrical parameter. So what is important? K1 is the stress intensity factor, so means what is the stress field at the crack tip. It depends on two factors, the applied stress and the crack size. And so what we said generally is when K1, so this stress field, reaches a critical value, K1C, then there is crack propagation. And so this is the local approach of flow and crack propagation. There is one second approach, which is called the Griffith thermodynamical approach, and we obtain the same type of results. In this approach, we consider a flow here, and we say, what will be the change in the free energy of the system, because it's a thermodynamic approach. What is the change in the free energy of the system when the crack propagates from here to this region? And if we plot the variation in energy versus crack length, we have two aspects. First, when you apply a certain stress to this sheet of paper, you store some elastic energy. So when the crack propagates, you have a mechanical energy release, since when it's broken in two parts, there is no more stored elastic energy. So it's beneficial for the crack to propagate, to decrease the stored energy. But on the other side, you create new surface. The larger the crack, the larger the two surfaces that has been created. So all in all, you have a curve like that, which is increasing for low crack size and decreasing for small crack size. And so, of course, one system wants to go to a decrease of the free energy. So if we are in this region, the crack should heal, because you have a decrease in the energy while decreasing the crack size. But for a crack above this critical value, an increase of the crack size leads to a decrease of the free energy. So we have two situations for a given applied stress. For a low crack size, so if the crack size is lower than a given value, healing should be possible. And we have observed healing in some specific single crystal or some glasses. Healing is possible. So for an applied stress, a crack can heal if the crack size is below a certain value. What is important for us in practice is for a crack size above this critical value, then you have crack propagation, which is beneficial for the decrease in the free energy. So what we said is that if the mechanical energy release rate is above the surface energy, creation of two surfaces, then we have crack propagation. And this is the Griffith criterion. And it has been applied in tension, so I don't want to go into detail in some aspects, but here is the evolution of the elastic energy which is stored in the system. Here is the evolution of the surface energy which is created, so it is directly proportional to the crack size. So here is the overall free energy variation. And so we said, okay, we have a given defect. What is the stress necessary for the crack propagation? And we found something like that. The formula was already presented by Gilbert. The strength, so the stress necessary for the crack propagation, is inversely proportional to the crack size. And so we have a good agreement between the thermodynamic approach and the stress intensity factor approach. Because we have seen with the local approach that the strength is inversely proportional to the crack size at the power 1/2. And we have the same for the thermodynamic approach. And we can say also that the toughness is related to the Young's modulus and the surface energy. So the resistance is directly linked to the surface energy. I can maybe pass through this because Gilbert already showed these pictures. I would like to go towards what are flows, but before showing flows, I just want to give you one example of processing. It is the processing of ZTA thermal heads. So this is a composite of alumina and zirconia powders. So when you have something like that, you make first a slurry preparation. So you have to mix these two powders into water with a given dispersant. You have already some presentation dealing with dispersion of ceramics and nanoceramics. And then generally at the industrial scale, you make spray drying. So spray drying is, so you have the powder which is dispersed in the liquid media, and you form granules, spherical granules, to be able to have a flowable powder. So here are some granules which are obtained via spray drying. So in practice, you have the slurry, and so you have a spray of this slurry in hot atmosphere, and then you obtain granules, agglomerates, which are spherical. And then this powder is really flowable. This is the powder. This is the alumina powder, which was obtained by spray drying, and you can see it flows very easily. And then, with this powder, you can make components. But if you look at the granules, they can be round, but either full, or sometimes there is a hole inside. So this means that we can have some defects inside the granules, even if they are round. And this is an example of, let's say, empty granules with a hollow inside. And then you make cold isostatic pressing, sintering. For thermal heads, you make hot isostatic pressing to decrease the flow size, to increase the density, and then polishing, and then grinding. So you have to grind the pieces. And so, if we now think about the defect you can create during the processing, I'm sure that the expert on processing will say, oh, that's a bad work, and this is really large defect. But these are defects, for most of them, I found on industrial parts. So real, let's say real parts and not small specimens. Here is a defect on a body densified, but which was processed by slip casting. Here is a defect which was obtained after gel casting procedure. So what you can see is that with these two techniques, you can create defects of some dozens of microns in size. Here is a green body of aluminum nitrate. So it's a green body obtained from cold isostatic pressing of a spray-dried powder. So it's a critical case. Here is a lab scale samples just to show that with these granules, which were too strong, it was impossible to press them correctly, so they do not deform, and the green body has a lot of defects of that kind. Here is an alumina zirconia composite, and we can be happy and can publish a paper in which we said we have a very nice, really nice, homogeneous ZTA sample. Here is the alumina, here is zirconia, and said, okay, that's fine. But just look in another location of the same sample, you have the defect like that. In another location, you have the defect like that. The ZTA samples were processed by cold isostatic pressing of a spray-dried powder, so we have defect of that kind. There was a granule, there was another granule, not completely packed one to the other, and then during sintering you create this kind of defect. And again, by this process, you have defect of some dozens of microns. Here is a sintered alumina. This is an implant. You have a region which is really dense, so well packed, well pressed, and then densified. But in one location, you have something like that. Think about the granules. There was one granule which was not completely pressed, and so the sintering in this part was different from this part. And so you create, again, a defect. That's not really a hole, but that's a defect. Again, 50 microns in size. Even if you process very well, you have grinding. So this is the dry grinding. This is grinding under lubricated condition. This is sandblasting. For example, for some implants, we need sandblasting. You create defects much larger than the microstructure of your body. You can have also some inclusions. Here is an alumina, femoral heads again, and we have tested 7 femoral alumina heads, and this is the number of the head, and this is the load to failure. We had one head that was lower in terms of fracture load compared to the others. Let's look, is there a defect? We take the femoral heads, one part, and said, oh, maybe there is something here. And then we increase the magnification, and so there is something like that here. And at high magnification, with backscattered electron images, we see a zirconia granule inside an alumina. So this means that in the same company, people were dealing with alumina, with zirconia, and only one granule was in the alumina powder, and it was the origin of this failure at low load. And so different types of inclusions. So this is an inclusion with a high thermal expansion coefficient, and so during cooling after sintering you have cracks. Here this is the inverse. You have an inclusion, and during sintering it shrinks. So you have something which creates a pore like that. We were talking about dispersion of slurries and so on. I think you were discussing about that in previous talks. You have to use grinding media, and sometimes it happens. You have a grinding media, a pollution, which is inside your ceramic. And so this is a pollution of few microns, but this is enough to critically decrease the strength. And then you have sintering. So let's talk now about submicron nano-ceramics. Of course, you can play a role on the defect by the grain size. Here is an alumina with a heterogeneous large grain size. You have defects of that kind. And we said, okay, the defect created after sintering are proportional to the grain size, as said by Gilbert, few times the grain size. So decreasing the grain size should allow to increase, but in the best cases, if everything is okay before that step, should increase the strength. So this is a poorly sintered, really poorly sintered ceramic, industrial ceramic, also for this one. And this is abnormal grain growth in an alumina ceramics. So we have seen flows due to the processing. So what is the effect on the strength grain size relation? So I take the same formula as Gilbert. There is a relation. Sometimes I say this is a belief. Often presume the defect size is proportional to the grain size. So we consider that the crack size or the defect size is proportional to the grain size. So there is a kind of Hall and Petch equation, since the strength should be proportional to the inverse of the square root of the grain size. Does it work? Gilbert showed us that for micron size, so size higher than a micron, it works. Does it work for lower grain size? Because we are now talking about nanoceramics. So here is a strength versus grain size graph I have plotted yesterday night with two independent studies on alumina. So one study with these dark black spots, and another experimental work with these blank spots. So if this equation works, we should have on a log scale a straight line. And the slope should be 1 upon 2, minus 1 upon 2. It works for large grain size, larger than a few microns for these experimental results. But when you reach low grain size, it seems that for these two examples, and people have worked well, that there is no more increase of the strength, decreasing the grain size. And that's quite obvious to me. The critical flow is not related to the grain size. It's related to something else, agglomerates, bubbles, defect created grinding. So this means that this relation works if everything is perfectly fine for all the different steps of processing. Okay, now let's talk about the defect related to the grain size, but that does not work properly for very small grain size. The defect is not related to the grain size for nanoceramics. So, also to insist on that point, I have plotted here this arrow in which you have, for alumina, we know the toughness, for a given flow size, what should be the strength? So this is flow size, strength for alumina. If you have microcracks due to grinding, you have large defects, hundreds microns in size. That's quite critical since the strength will be 200 megapascal. If you have organic compounds, debinding, agglomerate defects due, for example, for spray drying, it's some dozens of microns. You reach 3, 4, 500 megapascals. And we are quite here in average, in the real life. If we take the best conditions, 7 or 800 megapascal, we have defects of 10 microns, much larger than the grain size. So this means that the grain size is not really the defect created. And so we should say, okay, if we decrease the grain size with nanoceramics, we should obtain defects really low. We should obtain strength much larger than some gigapascal. Do you have ever reached this several gigapascal? I don't think so. I don't think we will reach this value for nano monolithic ceramics at least. So there is a limit in the strengthening by grain size reduction. So I have still 6 minutes to go. Yes, 6 minutes, hein, Gilbert. So let's move to the toughening strategies. Increasing the strength, you can either decrease the defect size or increase the toughness. So how to increase the toughness? So of course, by nature, we have polycrystalline ceramics, so there is always a certain amount of deviation. That's why even brittle ceramics have larger toughness than glass, for example, because we have deviation of the crack due to the microstructure. But we have also the possibility of bridging and also the possibility of phase transformation. So I will insist in these 2 points: elastic bridging, reinforcement and toughening due to elastic bridging, and also phase transformation toughening. The idea of all these toughening mechanisms is to increase the energy necessary for crack propagation, or let's say, increase the apparent toughness of the material. So we have the same data with Gilbert, so we can share this, but in a different way. These are the 3 ceramics you have shown before, and this is an increase of the energy to failure versus the crack length. The idea of bridging is that a crack won't go directly through the specimen, but there are some grains that are unbroken, and this unbroken ligament acts to close the crack. So the larger the crack size, the larger is the bridging. Of course, the larger the grain size, the larger the bridging. So this is the alumina we have seen before. This is a grain which is only partially broken. This is a grain which is not broken at all. So they act to close the crack. It's also operative, so this is alumina. It is also very well operating in silicon nitride. And so increasing the grain size increases the toughness. Let's talk about K1C. For submicron alumina, nano alumina, we only reach 3 to 3.5 megapascal square meter. For large grain size alumina, you obtain few microns. So toughening is increasing with grain size. So I would say for the nano ceramics, unfortunately, increasing the grain size and or aspect ratio will decrease the strength since you have large grains. But let's talk about this quite new result. Bridging is possible also in nanocomposites. Not in nanoceramics, but nanocomposites. And this has been quite nicely shown by Pature and co-workers in a recent paper with carbon nanotube inclusions. So let's talk about this composite. This is alumina, and it's inside the grains, and at grain boundaries, there are some carbon nanotubes. And these carbon nanotubes are able to bridge the crack. So here is a crack, and you have bridges with these carbon nanotubes. So you can have bridging in low grain size nanocomposites. So it's possible to have bridging and toughening by this bridging in some specific nanocomposites and not nanoceramics. So let's talk about transformation toughening. I think most of you knows about that, but just remind you that we have a crack and we have a zirconia-based material. In the vicinity of the crack, you have phase transformation. This phase transformation leads to volume increase in the vicinity of the crack, and so you have compressive stresses that act to close the crack. So if we have the stresses at the crack tip, so these are the stresses at the crack tip. So without any transformation toughening, we have something like that. With transformation toughening, you decrease the stresses at the crack tip because you had some compressive stresses. So the real stress field is now like that. So give some numbers. Cubic zirconia without any transformation, 1.5 megapascal square meter, slightly larger than glass. Mullite alumina, no transformation toughening, low toughness. White ZP, zirconia doped with yttria, large toughness, and larger toughness even for ceria stabilized zirconia with a toughness of about 10 megapascal square meter. So we can have also phase transformation toughening on nanoceramics. Here is again a quite new result from Biner and co-workers. They show that for a 1.5 yttria doped stabilized zirconia ceramic, for low grain size, this is much less than the micron, some hundreds of nanometers in size, we still have phase transformation toughening. So phase transformation toughening is also possible for nano zirconia ceramics, depending on the grain size and depending on the alloy content. What is interesting is that toughening, transformation toughening, leads often also to strengthening. Here is an example we have studied, 1 or 2 minutes and that will be finished. But so here is an example of a ceria stabilized zirconia alumina composite. So we have studied this during the NanoCare project. So it's a low grain size ceria stabilized zirconia plus an alumina composite. Here is the probability of failure versus applied stress for ground specimen, so really hard grinding, and then for specimens which were ground, then anneal to completely anneal the effect of the phase transformation. So first look at the numbers. Applied, the mean strength is about 1 gigapascal for this composite, large toughness, large strength. And if you anneal, if you decrease the effect of the phase transformation toughening, you decrease the strength. So low grain size, high toughness, high strength, and tetragonal to monoclinic phase transformation, high strength and high toughness. So that's possible with nanocomposite to increase both strength and toughness. So let me conclude about this first talk. Strength, I hope you agree, in ceramics is directly linked to the flows created during processing. I would say, in general, for real parts, for real specimens we have to use at the industrial scale at least, the flow size is much larger than the grain size. So there is a limit of the strengthening approach by only grain size reduction. Nanoscale monolithic ceramics do not exhibit exceptional strength, and we won't wait for an exceptional strength with nanoceramics. But playing with nanocomposites, then we can have some toughening, also by bridging. Phase transformation toughening, also applicable. And also, I will discuss in my second talk about the effect of residual stresses. So that's all for this talk. Thank you.